Hello and welcome to track 2 of the Plone conference 2020. Shortly we will have the talk about Pyruvate, a reasonable fast non-blocking multi-thread WSGI server from Thomas Schorr. And I will give this to our speaker, sorry.
Hello, everybody, and thank you very much for having me here today. My name is Thomas Schorr. I'm a freelance software developer from Freiburg in Germany, and I'm working with Python since over 15 years. I'm also a contributor to both Plone and Zope, about 10 months ago, I started a Rust project that I want to present in my talk today. And the title of the project. The project name is Pyruvate, and it's a whiskey server that I started to build in Rust. Let's start with a quick glance at Python enhancement proposal 3333, which is specifying the Python web server gateway interface, aka whiskey. The basic message of the PEP is that you can define a Python call level with a specific signature that will be called by a server software, the whiskey server, once for each HTTP request this server receives from a client or upstream web server. And this Python call level, the whiskey application, returns a set of headers along with an iterable response that will be rendered into an HTTP response by the whiskey server. And what we can see on this slide is the simplest possible whiskey application. And of course, it returns a hello world message in plain text. Instead of a list, it could also return some other iterable. When we look at the server side, then the server invokes the application call level once for each HTTP request it receives. I've already said that. But there's actually many possibilities for handling those requests. The server could be implemented as a single-threaded server. It could spawn a thread for each incoming request. It could use one-to-one threading or one-to-n, aka queen threading for doing that. It could maintain a pool of worker threads, or it could do Python multiprocessing using the Python multiprocessing module from the standard library, and it could do other things. The whiskey server can give hints on how it's actually handling the request through the environment dictionary. There are some keys related to request handling, but whether the application makes use of those hints is totally up to the application. And for example, in Zope, I could not find any hints that Zope is making use of those handling hints. On the other hand, on the application side, we normally don't have that simple hello world application. We often have a need to connect to components that outlive the single request, like databases or caches. And those database or cache connections might not actually be thread safe, and setting them up might be expensive. And all of the above is true for Zope, because SUDB connections are not thread safe, and they're also quite expensive to set up. So now there's a recipe for disaster when choosing a whiskey server that uses an inappropriate worker model, so one that does not fit your application and your application connections. As a consequence, although there are quite a lot of whiskey servers around, we have a fairly limited choice of whiskey servers that are actually suitable for Zope and Plone. So there's Waitress, which is the default, that has a very good overall performance. and it's a pure Python implementation. Then there's Björn that some of you might have heard of, and it's a C implementation. It's quite fast. It's using non-blocking I/O, and it's single-threaded. Then there's maybe some UWSGI options that could work with Plone and Zope. And yes, there are some other options described in the Zope documentation, but that don't have a very good performance. So eventually I wanted more options. So more options, please, for WSGI servers that are suitable for using with Zope and Plone. So I put up my personal wish list, and I wanted a multi-threaded server doing one-to-one threading using a worker pool, because that is the threading model that is working with Zope. I wanted a PasteDeploy entry point because I like that on Waitress. It's very cool because it makes WSGI servers a pluggable component that you can exchange easily. I wanted it, of course, to handle the Zope Plone use case. I have other use cases for WSGI servers as well, but I wanted it to handle Zope and Plone. And I wanted non-blocking I/O. And I wanted a file wrapper supporting sendfile, which is two features that Waitress doesn't support. And of course, I wanted it to be performing well. I'm not actually, this is not about creating the fastest WSGI server around, but I wanted competitive performance so that it's actually usable. Non-goals of the project are Python 2, because Python 2 is out of support. And then another non-goal is currently ASCII, not yet at least. So maybe in a couple of months, it might be interesting. It might be an interesting feature. And Windows is also a non-goal. I decided to use Rust for the implementation because I was interested in trying Rust for a while, and I had some naive expectations. I expected it to be faster than Python. So in runtime performance, I expected it to be better than Python, and I expected it to be easier to use than C. Let me elaborate a bit on Rust's performance. At the end of 2018, I've seen a talk by Paul Emmerich from Technical University of Munich, and he was comparing network device drivers for a specific network card implemented in different high-level programming languages. His argument was that high-level languages are safer, but he also wanted to assess the performance penalties that are coming with runtime safety checks and garbage collection. So computer science students could apply for implementing a user-space network card driver in a specific high-level language, and that would be their thesis. And in the project, they benchmarked each driver, and the chart you can see on this slide is one such benchmark result. And what you can actually see is that there is, of course, the very fast native C implementation. And then next, it's Rust that is following. So here we can see packet rate, so batch size and packet rate benchmarking. But there's a couple of other benchmarking results, and they all look quite the same. So Rust's always very much on top of when it comes to performance. There's one very specific feature of Rust making it both a safe and a fast language, and that is called ownership. So Rust has its own very unique implementation of memory management. And it's basically a set of rules that the compiler checks at compile time. And there are three rules. So each value in Rust has a variable that's called its owner. And there can only be one owner at a time. And when the owner goes out of scope, the value will be dropped. And now dropping actually is a trait. So a trait being the Rust version of a interface. And there is a default implementation for dropping a value, and you can override it. So, and also you can still control in Rust where your data is stored. It's a systems programming language, so it allows you to do low-level tasks, and you can control where your what kind of memory you are using for your data. And how is that relevant for safety and performance? And as an example, I want to quickly look at building a Rust extension for Python. So it's about interfacing with Python. When we look at Python memory management, there's reference counting and garbage collection. So whenever you assign an object, then you increase its ref count. And internally in the C API, there is a macro called pyingref that is invoked for increasing the object's memory reference count. And these pyingref invocations have to match with pydecref invocations, so decrementing the reference count. And garbage collection occurs when an object's ref count goes to 0. And if pyingref and pydecref invocations do not match, you'll see memory leaks and eventually core dumps. Now, as an example, if we look at well-known Python C extensions that we all use, then we have 63 occurrences of pyingref in B trees, which is part of the SUDB, and we have 19 invocations in Zope interface. And if we compare that to the Rust CPython Rust crate that is implementing the Rust CPython interface, then we only have one pyingref invocation, and the corresponding pydecref is implemented in the drop trait for the Python object wrapper. And as a result, it is very hard to create a mismatch of pyingref and pydecref invocations when doing a Rust extension. So you're very well set up to create memory safe extensions. And it's getting harder to create memory leaks or core dumps. Of course, it's still possible to create more references that you actually need. And of course, you can still create core dumps by, for example, not fetching Python errors from the error stack. Other Rust features that are cool include strict typing. There is meaning you will find many problems at compile time, and pattern matching is really cool. Rust documentation is very good, and there are very helpful compiler messages. And yeah, there's a couple of other good stuff about Rust. So let's start having a closer look at Pyruvate from a user perspective. So from a user perspective, at first, it's a package that is available from PyPI, from the Python packaging index. And so you could do pip install Pyruvate. And then it's an importable Python module. So writing your WSGI application, you would do import Pyruvate, then you define your application callable, and then there's basically one single function that you can use from this module. It's called serve, and you pass in your application, you pass in a socket to use, and you have to mandatorily pass in the number of workers that you want. So now, since this is Zope and Plone, most of you will want to use Plone recipe Zope 2 instance with setc buildout. And so in your buildout.cfg, if you want to use Pyruvate instead of the default waitress, you add it to your X sections, and then you basically use a specific WSGI init template and that you can pass to Plone recipe Zope 2 instance. And essentially in this template, you have a server section, so server : main, and you specify the Pyruvate PasteDeploy entry point. You specify the socket and the number of workers you want to use, and that's it. Let's have a look a bit at the project structure. Pyruvate is hosted on GitLab. I initially created it with cargo new --lib, so cargo new being the equivalent of cookie cutter or Bob templates. And with --lib, you will create a Rust library. So you end up having a shared object file in Linux. Then there's a src folder containing the Rust sources. Then there's this cargo.toml that's created by cargo new, which pulls in all the necessary Rust dependencies. There's a setup.py that you have to add yourself when writing a Rust extension, and you need to use a package called setup_tools_rust. And it's very easy. When you use it, you get a class named Rust extension, and it's very easy to define your Rust extension entry points and essential compilation options. And it also defines the PasteDeploy entry point. Then there's a PyProject.toml file to specify the build system requirements, which you can look this up in PEP 518. And there's a tests folder, which is currently containing mostly Python tests. So these are tox tests. I'm using py.test and tox to run the Python tests. And the unit tests, they are in the Rust modules. So they are in-module unit tests, which is one standard of writing unit tests in Rust. Then there is a _init __.py file in the Pyruvate folder, which is actually the function definition of the PasteDeploy entry point, and you import the file wrapper that you need for the WSGI file wrapper feature. And yes, I'm running a GitLab pipeline for the project with 2 stages. There's testing and there's a build stage for building binary packages. Part of the test is linting, so I'm doing a Rust format, which is opinionated code formatting in Rust, making Rust code formatting very simple because you just use Rust format and then your code is formatted the way it should look like. I'm sorry for that. And then there's Clippy, which is a Rust linter giving you hints on how to improve your code. Then I'm running the actual unit tests. And I'm creating a coverage report using kcov, which is a coverage creation tool working for compiled languages. And I'm uploading the coverage to codecov.io because at the time when I started that project, codecov.io was the platform that explicitly supported Rust coverage, and coveralls.io didn't say so at that time, at least. Then it's running the Python integration tests with tox, as I said before, for all available Python versions. And finally, if all tests pass, then I'm building wheels, so binary packages. I'm currently building many Linux 2010 wheels for Python 3.6 through 3.9. And I'll switch to many Linux 2010 after many Linux 1. After the stable Rust that I'm using to build the wheels stopped supporting the old ABI. So there was an error when loading the Rust shared libraries. Since Rust version 47, I think. And so I switched to many Linux 2010 because I did not want to go through compiling my own tool chain in a many Linux 1 Docker container. The important thing to note about many Linux 2010 is that you will need recent pip and setup tool versions to make the package work. So pip version greater than 19, So if you're doing a pip install Pyruvate and pip prefers asdist over real, which you will find out when it tries to invoke the Rust compiler, and then there's no Rust in your platform, then you need to upgrade pip. Same for setup tools when you're using it with setc buildout. You need setup tools version creator 42. And yes, and what's wanted is, as for binary packages, Mac OS. I don't have a Mac myself, so if anybody is interested in sending me a pull request, actually there should not be much difference compared to Linux. Maybe the sendfile call is different on the Mac. Okay, so let's do a quick run through the features. It's a Rust CPython based Python interface. So Rust CPython is one of, I think, 3 currently available Rust Python interfaces, and I found it to be very suitable for this project. Then I'm using a Rust crate called Metal.io, so MIO, which is part of a bigger project called Tokyo RS, and it's providing non-blocking I/O. Pyruvate is giving you non-blocking read in all cases, and then optionally blocking or non-blocking write. The default is non-blocking write. I'm using a worker pool based on thread pool, which is another Rust crate doing one-to-one threading. I said before that I'm having a PasteDeploy entry point. Pyruvate is integrating with Python logging. So I'm doing asynchronous logging, which means when Pyruvate is creating a log message, it doesn't need to hold the global interpreter log. And it also means for you that you can specify the logging configuration for Pyruvate in your whisky.ini if you're using Plone and Zope, or just any other way that is specified in the Python logging documentation. You can use TCP or Unix domain sockets, so IPv4 or IPv6 sockets and Unix domain sockets. And it also supports systemd socket activation. That's not easy to use out of the box with Zope and Plone, because you need the PID, the whiskey server PID, to look up the sockets, and that's not quite easy to do with Plone recipe Zope 2 instance. Yes, I started to look at performance, and it turned out to be a rabbit hole. So performance as in number of requests and amount of data transferred per unit of time. And I wanted, of course, to test it and eventually improve it. So my approach was first static code analysis and refactoring. That was very helpful because Pyruvate really started as a Hello Rust project. And so I found out, for example, that memory allocations are pretty expensive, which everybody everybody else might already know. Then I struggled a lot with how to actually induce socket blocking. So on a normal Linux, it's not quite easy to induce to see a socket that is blocking on write. So if I eventually resolved to limiting socket buffer sizes on a vagrant box for testing purposes, that it would be good to have that with Docker, but I couldn't find a way yet to do that because socket buffer sizes are basically specified on the host, and it would be good to have to be able to manipulate them on the container, of course. I've been looking at flame graphs from PerfData. PerfData is a tool that is collecting performance data on Linux. So it's actually looking at the time that functions spent on a stack, and that proved very good. It's very good to very good way of assessing performance issues. So, for example, I found out stuff like I found out that a call to two lower is much more expensive than a call to two ASCII uppercase. So, and I could eventually switch that. And I started doing some load testing with CH and AB, so Apache benchmarking, which is a very old performance testing tool. AB will always ever fetch one URL where CH will download the whole page. So yeah, it's quite different approach of testing. And yeah, I want to a quick glance at some design considerations that are affecting performance. So first, there's the Python global interpreter lock. So Python code can only run when holding this global interpreter lock. It's like a baton in a relay race. So if you have multiple workers, they really need to acquire the global interpreter lock in turn. And the approach is, of course, to acquire the global interpreter lock only for application execution and dropping it when doing I/O. And there's actually more than one possible way to do this. So yeah, I'm not quite sure yet what is the best way of doing it. Another another important issue is I/O event polling. So this MIO crate that I mentioned earlier is presenting an abstraction called a poll instance, which will do the necessary system calls. And so whenever the server accepts a connection, these connections get registered for read events with such a poll instance in the main thread. And so we are doing non-blocking, right? So it could take multiple turns to read the entire request, but eventually we'll pass the completely read requests plus the connection to the worker pool. And the free worker will pick up the connection along with the request, and it will invoke the WSGI application. It will iterate over the WSGI response chunks, which will need the global interpreter lock. And now, if you're doing blocking right, you can simply loop until the response is completely written, which is easy. But in the non-blocking case, you will be able to write until there is a E would block or E again error raised by the operating system. And I'm resolving to, when that happens, register the connection for write events with a per worker poll instance. So there's actually not one poll instance, but there's two. One is for read events in the main thread, and then each worker's got its own poll instance for write events. They're not very big, so this isn't, I'd say, overly expensive, but there could also be other options for doing that. And yeah, once I receive E again error, the worker drops the global interpreter lock and will stash the response for a later write until it receives a writable events from the per worker poll instance. Yes, so first performance results on my Lenovo X390 and a Vagrant box. So I'm doing it both natively on the laptop and a Vagrant box with 2 CPUs, 2 gigs of RAM, and 8K write buffer size limits, which is really small. So it's a lot faster than Waitress on a Hello World WSGI application. and it's still faster than Waitress when downloading slash URL. So, so in this case, looking at the test criteria for benchmarking whiskey servers from the Zope documentation, but it's currently slower than on slash Plone. That's interesting. I'm still investigating. I don't know why that is, and also I'm sometimes seeing contradicting results. So there's definitely more performance testing needed, and there's a lot of different situations and still a lot of different possible combinations of setting up, like number of threads and so on. And yes, I'm only starting to assess that. Okay, let's do a little live demo. I've prepared a build out that I've already run, which is defining a Pyruvate, a Plone instance using Pyruvate. So there's a CO server, there's a Plone instance using Pyruvate, and then there's another instance using Waitress. They are running on different ports. So the Pyruvate instance is running on 7878, and Waitress is running on 7879. CO server is already running, and I'm starting Pyruvate. It's telling me it's ready, and I've prepared a browser tab for running this, and database is empty, so I'm prompted for a new Plone website. I'm creating a German site because I'm German, I'm used to German. Yeah, looking at the console, it's running that. I get Plone. I can browse a bit. I can upload a file. I'm uploading the Rust programming language, documentation. It's taking some time because it's rather big, but eventually it gets uploaded. I can download it. I could open it, yeah, in a PDF reader. Let's maybe have a quick look at the CMI. So going to the control panel and going to the databases control panel, I can see that there's 2 database connections at the moment, which is corresponding with the 2 worker threads that I define in the build out. When I reload, I see that these are always the same 2 connections, because the application, the whiskey application, gets copied to each worker thread, and then once upon startup, the connection will to the SUDB connection will be opened, and it will be reused all the time. Yes, that's basically all there is to see. It's just Plone. This is Plone 5.2 latest, so it should be 5.2.3. I've built it on Saturday. And what I can do now, after browsing a bit, is I can do some load testing, like specified in the Zope doc. I'm doing it like specified in the Zope documentation. So 100 concurrent clients accessing Zope. I'm not running it for 100 seconds because that would take too long. I'm running it for 30 seconds. And yes, while I'm doing that, we could actually already, I think, I'm going to do the same thing with Waitress later on, just to get a comparison. But while I'm doing that, we could maybe already have questions, if there are any.
No, at the moment there are no questions.
Okay. So I'm starting the waitress instance. And we are seeing waitress starting up. And to be fair, sorry, that was the wrong page. And to be fair, I'm going to browse a bit on this page just to warm the caches, of course. And then I'll do the same thing for the waitress instance. So we can get a comparison on performance, which is of course, I am biased, of course. And as I said before, there's different results for different URLs. So you definitely have to do your own benchmarking if you want to pick a whiskey server. So what we can see here is that, hang on, where are we? So there is 5,809 complete requests in 30 seconds. And here we got 8,171. So this is Pyruvate, and it's got a couple more completed requests. None of the servers had failed requests, and corresponding with a bigger number of completed requests, there's more data that has actually been transferred. Yes. Okay. So that so much for the demo. Yeah, that's basically what I wanted to tell you. I'm planning a 1.0 release for end of this year. There's a couple of things that I still want to do. Currently, we are on version 0.8.3 on PyPI. It's still a beta version, so it will have bugs. But yeah, I'd be happy if you want to give it a try. There's a feature branch on GitLab that needs some work, which is implementing keep alive and chunk transport, and that I want to integrate in the 1.0 release. Then, as I said before, I want Mac OS support. That's still open. I want to optimize a bit the pipeline. For example, I'm currently compiling the kcoff binary each time I am running the coverage reporting, because there is no kcoff binary package available for Debian Buster, which is the base image for Rust Nightly. And then I want to fix an issue with the thread ID that is not reported correctly when doing async logging. And of course, I'm doing more testing, and I hope that I can fix a couple more bugs. And that's it. Thank you very much for your attention. And yes, if you want to give it a try, I'd be happy for feedback, for your feedback. I'm looking forward to your feedback. Thank you very much.
Thank you, Thomas. There was one question in the Slido. I guess it's kind of answered. The question was, is it a project to keep an eye on, or is it ready for production yet?
It's better. I'm using it in production on a couple of smaller sites, and you can definitely use it for development as a drop-in replacement for waitress, and I think you also can use it for testing. And I think it's not a replacement for waitress, it's an alternative. So it's got a couple of features that are the same, which are the features that you need to make it suitable for use with Zope and Plone. And then you got a couple of different features like non-blocking I/O. Yeah, and that makes it a bit different from Waitress. So you might want to try it in different situations, or you might just want to compare it. But I think you can start. Yeah, start. Yeah, start. I started using it in production.
Okay, then thank you from Vincent for this answer, and thank you, Thomas, for the talk. I would encourage everyone to come to the face-to-face. You can find the link down below under the stream just by click on join face-to-face. And yeah, we have a break on this track, I guess, for nearly an hour. So see you back in an hour, hopefully. Thank you.
Thank you.